Welcome to Spring LIB.
Okay, we've got a number of carbocations we need to rank. And we've got a carbocation here. This is primary, rather unstable. Got a carbocation here that is secondary, that is more stable than a primary carbocation, called due to hyperconjugation. You need to look up why it is that tertiary and secondary carbocations are increasingly more stable. And this final carbocation is tertiary. So this is the most stable, this is the least, and this is in the middle. So if we need to go low, intermediate, most, that would be 1, 2, 3. That's the answer. Okay, let's continue. Okay, now we have got this molecule, and we're going to react it with DBU. So DBU is a bulky base. It's a strong non-nucleophilic base. So we won't get any substitution. We'll only get elimination reactions. Okay, and the question is, what kind of products will we get? So I would think it would be wise here to draw the mechanism that would correspond. Right? If we do an E2, the proton will get deprotonated, leaving behind its electrons to form a double bond while the bromine leaves, yielding the following product. And the question is asking us, okay, this is A. Is there some way that we can get B, right? Now, you'll notice, B is actually more stable. It's more highly substituted. But that depends on whether there is a path to generating B, right? And I want to say, no, there's not, right? And the reason for that is that this carbon is primary, right? The only path I could see to B would be the following. I'll sketch this out and then explain why this won't happen. If this bromine leaves and generates a primary carbocation, we could potentially see migration of a proton to form the following carbocation, right? And if we deprotonated a neighboring proton now, we would have generated product B, the more stable product. The issue with that is that relies on bromine leaving by itself, which is not going to happen on a primary carbon. This step is a no-go. So for that reason, we should only expect A. All right, so the E2 reaction, no problem, primary bromine. The E1 reaction, where the bromine leaves, and then we see proton migration, is not really viable because we're at a primary carbon. It involves the formation of a primary carbocation, which is incredibly unstable. Okay. Now we've got a number of alkenes, and we've got to decide which is the most stable, so let me sketch these out here. And what we're going to compare these on is their degree of substitution. That is, how many bonds to carbon are coming from the sp2 hybridized carbons. So we can really just count here, right? I see 1, 2, 3 bonds to carbon, right? Coming from the sp2 hybridized carbons, which I'll circle in blue. sp2, sp2. Okay, so let's say sp2, sp2. I see 1, 2 bonds to carbon. Nope, that's not as stable. Recall, the more bonds that the sp2 hybridized carbons have, the more stable. So there's an sp2 hybridized carbon. There's another one. How many bonds to carbon? 1 and 2. All right. And we could continue on with this, but really we're just going to see there's 1 here and 2 there. And here there's, in fact, only the 1. Right? That's the only bond. And if you're wondering, like, well, this is hard to see, remember that these other bonds are to hydrogen. So you could also say the fewest bonds to hydrogen is the most stable. So 2 hydrogens there, 2 hydrogens here. Right. This one has the most bonds to carbon and the least bonds to hydrogen, so it is the most stable. Just the very first one they showed.